apologize. I sound like a frog today. I don't have much of a voice, so you guys might have to strain a little to hear me. This is the most I've been able to speak all day. So, but for those of you I haven't met, I'm Ani Morris. Just moved back here in April. I've been living in England for the last few years, bouncing around with the military here and there. I live over by Clayton now. So, they asked me to talk on narrowband imaging. So, I'm going to attempt to do. So first thing, I figured I'd start with the basics of what exactly is narrowband imaging. And I don't know, I'm assuming that you've listened to imager group, that most people do a little bit of RGB and narrowband, some planetary and whatnot. And basically narrowband is just going to be different filters that cut down, excuse me, the wavelengths that you see as opposed to the whole broadband of the red spectrum. You're doing very finite wavelengths within that. And some of the advantages of it is you get a lot smaller stars because where the emission nebulas and stuff are broadcasting their wavelengths is actually absorption lines for a lot of the stars. So in addition to getting all that extra data, you end up with a lot smaller stars in your images, which helps when you want to overstretch and whatnot. You don't have to worry about blowing out the stars. Also, you can mitigate the effects of light pollution, both man-made and lunar. So you can image a lot more nights throughout the month because the moon and a lot of lights and whatnot are very broadband wavelengths that they do. So cutting down to a finite wavelength, you only get a little bit of that energy passing through. So the contribution from the moon and what can the sky go ends up being very small. So you can even image half, 3/4, even full moon, depending where you're at, and still get decent shots depending on which filter you're using, and not have to worry about blowing it out like you would in RGB, where all you see is the sky glow. Another reason is you get unique palettes, unique colors that can show the different ionizations of the gases and the interactions of how these objects work together more than you would see in RGB. And next on to the most common filters that are used. Kind of the king filter for narrowband imaging is hydrogen alpha, which lets through a wavelength of 656.3 nanometers. And you can get various you get various widths for filters. So you can get one that's, say, 3 nanometer or 6 nanometer. And it's going to, the central point of them is always going to be the wavelength for this. And that'll come into play here.
Is there a cost differential between?
There is. Generally, the narrower, the more expensive.
Okay.
And it can get very expensive if you want very finite narrowband.
Does that also increase your exposure time?
It does, yes. Because you're letting less light through.
May I interject here? That was a question I had with the Astrodon filters, and the exposure time, I have the 3 nanometer I had the 5 nanometer HA. And they said that the exposure time is the same between the two. Maybe as it gets higher, further out.
It should be the same, because you get the Doppler shift to broaden your line beyond 30 angstrom, or 3 nanometers.
Right.
That's a lot of speed,
That's
right? I mean, you can't, especially in the oxygen one, but
right.
It does cut down on light from the stars, though. Right. Yeah, you can go back and look. A few years ago, the debate, Astrodon came out with narrower ones, and there was a lot of things.
Well, you benefit from, yeah.
But, I have heard both ways. I guess it depends on what do you mean by, is it going to have to do longer exposures? I mean, you can do the same exposures for both, but like you said, it's going to be letting less light through. So.
For more of the specific light you want.
Right.
So your signal noise is better, even at equal acquisition time.
Yes.
And if you want to do planetary nebula, you shouldn't really go any narrower than 5 nanometers because it's very close. If you went to like 3 nanometers on the HA, you would lose some of that capability of looking at it. Because the nitrogen line is very close.
Which is here as well, which I guess I'll jump down there. Yeah, the nitrogen is right near the hydrogen alpha. So if you have a 3 nanometer hydrogen alpha, is the only way to split the nitrogen off of there, which some people do use the nitrogen filter as well, which is why it's on here. But the 3 most common ones are the hydrogen alpha, the oxygen doublet and the sulfur doublet, which you can see there are various wavelengths here. Most all emission nebulas and whatnot are going to have a good bit of all of these, and I'll get into targets here in just a moment. A lot of planetary nebulas will have a lot of the O3 in them, so if you're going to pick two and like do a bicolor, hydrogen alpha and O3 are generally the most common ones to do that with. And sulfur is also in the red spectrum, as well as nitrogen. It's deeper red than the hydrogen alphas. So it's going to be hard to distinguish that when you're doing red filter, which is why you can see a lot more depth in some of these nebulas when you do narrowband, because otherwise, say like the North American nebula, when you image it in RGB, it just looks red, because it has all these various gases that are all in red spectrum. Yeah.
I was confused about my question, and maybe there's something fundamental I don't understand.
Yeah.
He's talking about 3 nanometers. You're talking about like the hydrogen alpha is 656
Yes,
nanometers. You're talking about 3 millimeters deviation on either side of the 656.
Yeah, so it'll be
Yes.
1.5 on each side.
1.5 on each side. The
Okay.
3 is going to be the total width
That's the
that the
band
filter
pass.
And how much do you through centered on that?
centered on this point
Exactly.
here. So on hydrogen alpha, it's centered on this. Oxygen has the two, excuse me, two different wavelengths that it allows through.
Hey Mark, do you know what periodic error is?
Yeah.
That's a good analogy.
Okay.
Oh,
Unless you have a marmalade by me.
Nani, real quickly, most of your
That many people do.
narrowband image is what do you use for HA, O3, and S2 for most of your work?
mapping it?
Yeah, no,
Or which filters are
Yeah.
used? The hydrogen alpha, the O3, and the S2.
And-
I don't have a nitrogen one. I know I have some friends that do, but I haven't.
do they
gotten
get
those
any
two.
good results? I mean,
They do different palettes, and a lot of them will do spectroscopy and all
Yeah.
sorts of.
are your
figuring out
stat
the
5
gases and
nanometer,
whatnot.
5 nanometer type?
Yeah, I've got 5.
Yeah.
And what about the makes of the filters? I mean,
I have astronomic. A lot of people use Astrodon, and there's a lot of different ones. And
They're all good.
yeah, I mean, well, they're not all good, but there's several good ones.
they're inch and a quarter, right?
I was real skeptical.
Everyone seems to
Yeah.
generally agree that Astrodon are the
Right,
best.
and I was skeptical about mine because I didn't think they could actually do that. So I took them in. I have a FTIR at work, and I put them in and sure enough, I don't know how they do it, but they were exactly what they spec'd them to be. I mean, I don't know
Well,
what.
getting also one of the big expenses is making them parafocal.
That's right. That was the
That
other
was
big thing.
the other
Parafocal.
I don't believe in that.
Big issues.
Yeah.
I
And
never
that's
said-
Having a refund.
What they
Well,
say
if you're
about
on a
parafocal,
wheel,
no,
it
that's-
is, but yeah.
But I have Astronomic, and they're a step down from Astrodon, but I mean, I compare them with my particular setup to the Astrodon, and I got the same results,
Yeah.
so I went with the slightly cheaper ones.
And they're parafocal after.
Supposedly, yeah.
Yeah.
So, I mean, just kind of whatever, because there's quite a range in prices and quality of them as well, so.
My spectroscope can actually tell you what you got. Because sometimes what they tell you on the box is not what the filter actually does. So if anyone's curious.
Well, that's why I
can-
put it in the Perkinomer FTIR.
Oh, so you've already done the analysis.
Yeah, I
on
put
yours.
it in, I took it to work and put them in there, each one of them in there just to see, because I have 2 5 nanometer and, I'm sorry, 2 3 nanometer and 1 5 nanometer.
That's easier than my solution with my spectroscope. But yeah.
I have a question. So we talked about how all this stuff filter out all the uninteresting things, light pollution, moon glow. It's moon glow that I'm most interested in as far as what it's able to attenuate. And I've read various websites like Cloudy Nights, for example, that you want your moon to be a certain number of degrees away from the subject you're trying to image. Now, I mean, what is your experience with that? Say like you have a full moon, quarter, half lit moon or whatever. I mean, what's your
Half-lit moon, I mean, I can shoot fairly close to me, any between half and full, I try to stay on the other side of the sky, but I mean, it's still a giant flashlight in the sky.
Okay,
So, I
well,
mean, you're
put you
cutting
on the
out a lot
spot.
of the
How far
wavelengths,
away
but,
from it? What would you consider the cutoff as far as a subject
A lot
that's
of that's
close
also
to
going to
moon.
depend on your system and how much light it's gathering. So if I'm shooting on my F10, it's going to be different than when I'm shooting out of F5. And it also depends on the filter too, because say you have a 3 nanometer hydrogen alpha, you can go a lot closer and cut down a lot more than the oxygen. O3 tends to let a lot more of that light through. And so like 5, even a 3 nanometer oxygen, it's still going to let a lot more of that than hydrogen alpha.
Because right now, it's like
So
you saw.
I know you're looking for degrees, but I don't know.
Yeah, well, that's fine. I mean,
Yes, in degrees, but
it's like what I'm doing now. You probably saw the M27 a long time ago. I think that was the first time you were here. Actually, the first channel I did was O3. This new one I'm doing, the first channel I did was O3, just because I'm, being cautious about what the moon is going to do.
Me personally, I don't like to shoot O3 more than half through, unless I'm on the complete opposite of the sky. It's just with my system, I get too much light in it. I'll shoot.
Is that from
hydrogen
experience
alpha.
or just
It's
you
just
being
from
cautious?
experience,
Or-
yeah.
Okay.
And I can still process it out, but it's a lot more processing, so I just try not to. I'll still shoot hydrogen alpha almost all the way up to the full moon. But I cut down on the subexposure length too, so I won't do hour-long exposures anymore. I'll maybe 20-30 minutes instead. So
Okay. Very good.
it's
Thanks.
just a little bit of trial and error from my system. So. Okay, next was picking targets and choosing which filters for them. The 3 main ones you'll want to use narrowband for are emission nebula. Obviously, being emission line filters, they're to pulling out the emissions lines in nebula. And they're really great for tricolor, so hydrogen alpha, S2, O3. A lot of people also use the nitrogen, depending on if you want to get into that realm or not. Good targets are any of the emission nebulas, North American Nebula, Heart Nebula, Elephant Trunk, etc. Excuse me. Planetary nebulas are also really good for narrowband, though some are better than others. You can see whether they're more emission or reflection in the planetary. Some have more reflection of parts, and you're not going to get as much advantage from the narrowband filters. A lot of them also have a lot of helium and neon lines in them, as well as a lot of nitrogen. So those other filters you can actually get a lot of use out of for planetary nebulas. Great targets there: Helix, Dumbbell, Anderson-Jones, Ring Nebula has a lot of hydrogen alpha in it as well. Supernova remnants, Veil and Crab Nebula. I've got the veil faded in the background there. They're great for using that. You can see a lot more depth in the objects than you would with RGB, just breaking out all the different gas lines.
Veil seemed to be, what would you concentrate with veil? Would you, what filter would you tend to collect more data?
Hydrogen alpha.
Hydrogen alpha?
Yeah.
Okay.
Like this one here is all narrowband data, but then I used RGB over it for color. So.
Is that only, that's bicolor, right?
No, this is
Really?
This is tricolor, and then I used.
Because I always see that done in bicolor, you know?
Well, I actually used all RGB data for the color,
Oh.
and then basically the luminance channel was a compilation of the narrowband.
All channels in narrowband?
Yeah.
Oh, wow. Okay.
6 channels.
Wow.
That must have been annoying.
Not feel good about that. But yes, they can't get into it. Yeah, what's really annoying is when I don't forget to turn off the luminance, and then I have the luminance channel that I basically am just filling out and wasting my time because I'm using the narrowband for that instead. So. Some reflection nebula, you can get some advantages with using narrowband. More you have to look at the object and see whether it has good bits of hydrogen alpha or oxygen in them. You can use those, roll the hydrogen alpha into the red, the oxygen into the blue, and pull out a little more detail than you normally would. Though some of them you're not going to see much advantage adding much. You kind of just need to research the object a little bit if you're going to look at a reflection nebula. Did you? Oh, sorry. And exposure times, typically a good bit longer for narrowband than RGB. Most of them aren't too much shorter than 5 minutes. Most people do up to 45 minutes, or even an hour, depending on the object and your setup. There are certain exceptions, M42 being one. If you shoot an hour on there, you're going to have an entirely white screen, which is not fun. But ones like that, we're going to have bright parts of it that blow it out. You do a lot of layering, so do a couple 30 seconds, minute, 5 minutes if you want to get the depth in there as well, but still have areas that you don't blow out, and then combine them all in post-processing.
What would be the max, I'm excited about trying to do M42. What would be the maximum time you would spend?
I've done 30 minutes, but I did it on a wider setting, so the whole core was blown out, but I wanted to get the outer bit.
Right.
So if you're like using a C8 or something, then in your Retina fusing, you're not going to get that.
Right.
Good way to determine sub-exposure length is do 1 minute or 5 minute test exposure bin, and then I'm going to pull up on the next slide, calculate how much sub-exposure time you can do without hitting your max ADU for your particular setup.
Right.
And then down here, I just reminding people who don't really know much about binning that binning 2x2 is going to increase the ADU count 4 times compared to an image bin 1x1 because it's pulling all 4 neighboring pixels into one. So if you're going to do a bin test exposure, calculate the time. To calculate the time for bin 1x1, you want to multiply by 4.
So divide by 4 if you want to do equal exposure of something that's 1 by 1. Is that right?
Yes.
Okay. One question about that. I see a lot of people do HA almost always 1 by 1. The other 2 by 2. Now, what's the harm in doing everything 1 by 1?
There's not.
I'm just like, well, what would the difference
I've had
be?
many debates with many people about that. It depends on what you want to use for the detail versus just color mapping and whatnot. Because the North American Nebula that I had on the front, the initial slide, was a 12-panel mosaic, but I shot everything in 1 by 1 for the hydrogen alpha. And then for the O3 and the S2, I did wide angle with my DSLR, actually. Well, not my DSLR, but an attachment from it there.
What kind of
so it
lens
basically
was
ended
that?
up being bin 3 for the hydrogen alpha for that, and I use the hydrogen alpha for the data. So, but if I wanted to have the depth of the detail for all of them, then I wouldn't want bin them unless you're going to scale the whole thing.
Very good.
So sky quality doesn't factor in when you're trying to decide whether you're going to, are you like in 6?
Well, it depends on how you want to scale it and what
Okay.
you want to use for your luminance
Oh, okay, okay.
as well. I mean, if you're going to keep all of them scaled the same and bin them all and then keep it all small, it gets a bit more complicated.
No.
Is that,
Sorry.
no.
Yeah, no, that answered it. That's where you're getting. One thing I had in mind as far as like if I were going to attempt RGB, don't get carried away, Mark. I'm still going to be a DSLR guy. If I were to do RGB, is it wrong for me to just, instead of just doing red, just do hydrogen alpha only and then green and blue? Or is that a big mistake?
I wouldn't say it's wrong. So if you're going to do that, then you're going to lose some of the wavelengths there.
Yeah, of course, yeah.
But I mean, but you can do that.
Because I mean, I look at galaxies and all I see is, mostly blue.
Yeah.
And
And
I mean, as far as red goes, yeah, it goes into, the lighter shades of yellowish orange, But I look at that and it's like,
I
well,
would
what's the
more
point
do
of
the
doing
normal
that
RGB and then take hydrogen alpha as well and add it to the red.
to the red? It wouldn't substitute for red.
No.
Because I've used HA in the place of the luminance channel, just to bring
Yeah,
out detail.
I'll do that all the time. But as far as, and you could do that, but me personally, I would add it to the red as opposed to replacing it.
Add it to the red or make it luminous to the red. I mean, luminous to all 3.
Use both, yeah.
Okay.
Math for all of those who like that. There are a lot of different ways to calculate your sub-exposure time. This is one that I like because it's fairly simple. And using a test exposure, you take it, you know the pedestal of your camera, and so you take your test exposure ADU, like pick the brightest star that's in there, subtract out your pedestal, then multiply that by the amount of time you want to shoot over the amount of time you did for your test exposure, then add back in. So say I did a 1 minute test exposure, and the brightest star was at 5,000 ADU. My camera is, say, has a pedestal of 1,000. So calculate that out, and I say I wanted to do a 15-minute sub-exposure and see if that was going to blow it out. Calculate it out, it would be 61,000. And my camera's max ADU is 65, 543, so the 15-minute exposure would be good. But I know that I couldn't do too much more than that.
Are you worried about saturating the stars? I mean, your nebula is at such a low level, you're going to have to go longer to get the signal to noise and get your read noise. So I'm curious why the stars are important. So you calculate the optimal sub-exposure just statistically, right? You're going to compare your flux in the nebula to your read noise and your sky background.
Yeah.
This might be heuristically be the similar answer, but I haven't seen it done this way before.
Like I said, there are a lot of different ways to do it. This is just one way that I go about doing it to see whether, and it's more if I'm going to actually try to keep, well, if I have brighter stars and I want to make sure they're not gonna have any blooming effects or whatnot from them oversaturating. And also same if I don't want to lose, say I'm also doing them with color data, I don't want to lose the color in them from them being oversaturated. Did that answer, did that make?
I just watched it talk. I'll ask you a question again.
Okay. So more common exposure times, generally 10-20 minutes for an F5 system, 15-30 minutes for an F7 system. These are just general guidelines. It ranges a lot, and depending on what you want to do as well. I've got F5 system, I'll do 30, 60-minute exposures sometimes in narrowband, depending on what I'm shooting. If I have a dark area that I'm not going to have anything that's blown out, I'll do as long as I possibly can. If sub-exposures do get too inconveniently long, or you don't have perfect guiding, you might want to bend so you don't have to worry about star trailing. Though I'm not getting into bending here, I'm not really big into bending, so that's just me personally with the narrowband. Unlike RGB images that are usually limited by sky glow, narrowband are limited by dark current noise for the most part. Because the exposures are 3 to 10 times longer than RGB, dark current should be tried to minimize as much as possible, so using active cooling and whatnot. And another rule of thumb is for every 4 to 6 degrees of cooling for the sensor, there's 50% reduction in dark current. Obviously it's depending on the camera and the system you have, but as a general average. So to increase your exposure time factor of 8, you're going to want an extra 12 to 18 degrees centigrade cooling to have the same dark noise current in your system.
Is that something you've observed yourself, or is that just what you've read? Sorry to put you on the spot.
A little of both, yeah.
Oh, okay.
Kind of an average of the both. And then palette selection is a big one for this. There are so many different palettes you can do. You can customize it however you want, really. There are a few more common ones. The most common is probably the Hubble palette, which is descending wavelength order. So putting the S2 in the red, hydrogen alpha in the green, O3 in the blue, and having, them all balanced out as you do that. Another one that's commonly used is the Canada-France Hawaii telescope, CFHT method, which is the hydrogen alpha in the red, O3 into the green, S2 into the blue. And then every once in a while I'll see someone do reverse wavelength order. So O3 in the red, hydrogen alpha in the green, into or the S2 depending which one you shoot, into the blue. You can also augment this with RGB data, or just come up with whatever you think looks good. Because if you're not doing RGB anyways, then it's all going to be false color. So however you want to play around with the channel mapping to make it